neural field equations for the rest of the week. Um, so it's something that I work on, but also I think it's a good example of kind of a canonical integral differential equation that admits a lot of the analysis that we've already talked about earlier in the semester. Integral differential equations are different from PDE because you have an integral operator instead of just a differential operator. You can also have differential operators, so you can have integral partial differential equations. But the idea with diffusion is that essentially if you have some substance that obeys a reaction diffusion equation, that it's going to react locally and then spread out according to diffusion. The idea with integral operators is that they can also transmit substance across long range, but in particular, they're non-local. So it doesn't have to be that just items move to adjacent regions the way that diffusion works, like how heat or temperature sort of spreads across a heated bar or something like that. Things can jump in space, and so an integral operator allows for a lot more flexibility in the kinds of communication or movement that you would have in a model. So the particular models that we're going to talk about are what are called neural field equations. If you come from a physics background, you might think, what does this field mean? Well, these equations actually were developed by statistical physicists in the 60s and 70s, and they used mean field theory in order to derive them from more detailed stochastic models. In the interest of time, and also given that some of you don't have the necessarily the background for us to just jump right into that, I won't go through the derivations, but hopefully I can give you some intuition for where these come from. So just like any kind of PDE model that we've written down this semester, or if you took PDEs with me, we have that some substance is changing in time, and it's going to decay. And then the way that the level of this variable changes in response to levels of the variable at other parts of the domain, which we'll just call omega for now, is given by this integral operator, the integral of the function wy integrated against u yt dy. And then we also have some non-homogeneous forcing term I of xt here. Okay, and so u is just equal to u of xt. X lives in some domain omega, which is a subset of Rn. We're mostly going to deal with subsets of R for what we're going to look at. And what this describes is the average activity of neurons at location X. Okay, so neurons are the fundamental cells that make up your brain and also your peripheral nervous system, and they communicate with each other according to a complex graph. If you want a model that's analytically tractable, one approach is to treat sort of a chunk of your brain like an excitable medium, and that is the idea of this model. So individual neurons, right, they're made up of a soma and axons coming out of them, like electrical cables. They're actually, biological electrically conducting cables, and what are called dendrites, okay, that are, like branches of a tree. The dendrites receive input, all those inputs converge in the soma, and if that's enough input to activate this neuron, it will send a message along the axons to other neurons, and this process continues many thousands of times a second as you're, sitting here listening to me. So, here's another neuron. It has its own dendrites, and the idea is that these axons, the ends of them interface with the dendrites through little gaps. So there's a little gap in between them, and when the electrical signal gets to the end of the gap, it activates chemicals that then diffuse across a gap in between the neurons and is uptaken by the dendrites of this cell. Okay, so this is, neuron 1, this is neuron 2. Okay, and obviously I could go on, drawing many thousands of neurons. You have 10 to the 11 neurons in your brain, okay, that are doing this all the time according to a complicated graph. All of that for our canonical model is going to be described by just this function W, which describes the strength and the sign of the connection from one neuron to another. So W of XY is going to be the strength and the sign of influence of neurons at location Y on those at location X, okay? And this is often called the synaptic weight kernel, okay? And a lot of times we take this function to just be a function of distance, okay? W of X minus Y, okay? And you could have a function that looks like this, W bar of X minus Y. Here's your function of X minus Y. And this would mean that neurons that are close to each other tend to excite each other. Neurons that are farther away from each other tend to excite each other less, okay? You can also have functions like this, where neurons that are very far away from each other tend to inhibit each other or prevent each other from becoming active, and neurons that are closer to each other will tend to excite each other. This is what's called a lateral inhibitory kernel, okay, as opposed to just an excitatory kernel here, okay? And just with these two kind of basic interaction patterns, of course, your brain is much more complicated than this. You can produce a lot of interesting patterns that are explanatory of many types of sensory processing in the brain. For instance, how you take photons in through your retinal cells. They get sent to the back of your brain, which is the main center for processing geometrical properties of vision. These types of interactions help to sharpen those images as they get processed in a feed-forward network that represents, different visual objects that you can recognize. All the shapes that you see and recognize, they are created by a network of neurons that's organized in space, okay? So that's why it makes sense to think of networks that really depend spatially, because there are spatial maps in your brain, in particular for things like vision and also audition as well, where there's a regular sense of the spatial features of the environment, where sounds are coming from or where objects are in the environment. Okay. All right. So now I'm going sort of rapidly through this. I just want to give you a flavor of where these models are coming from. And then lastly, f of u is going to be 1 over 1 plus e to the minus eta u minus kappa in our models, okay? This is what's called a sigmoid type function, right? Sort of looks like this. Here's kappa, here's our u variable is varying here, and here's f of u, okay? And so the idea is that this is called a transfer function. And again, those of you coming from physics, this may look sort of familiar. You see this in sort of ferromagnetic type models. I think, sort of generalizations of the icing model and things like this. And it converts the activity input to the output of connections between neurons. Okay, so it's meant to describe this complicated process of activity being generated here, providing input to dendrites. Of course, in reality, that should be represented by several nonlinear differential equations. We're just saying weak inputs will not have a strong effect on their neighbors, and strong inputs will eventually saturate the input of activity in their neighbors. Okay, because if this was unlimited, essentially you would explode neurons eventually. So there's some saturation mechanism that prevents neurons from sort of spiking endlessly. If that mechanism gets messed up, you have epilepsy, you have sort of uncontrolled spiking in the brain. This is where the genesis of seizures. Okay. All right, and then lastly, I of xt is what's called a spatio-temporal input. Okay, this just describes whatever external activity is coming into this network. Okay, so we're modeling the activity of a particular portion of the brain. This could be some input that's coming in from some other region of the brain, or maybe from the external world, like visual input. Okay, and so we just kind of want to study the mathematical properties of this network. I'll do basically a couple examples this week of the kinds of activity you can get. If you're interested in more, I have given some references in Canvas if you want to read more. Okay, and okay, so depending on the weight, okay, the transfer function f and the input, okay, we can have patterned, okay, where essentially you have neural activity that oscillates in space like this. We can have wave type activity, as we've seen in other reaction diffusion type systems, or what are called stationary solutions, where maybe we have some localized region of activity here that doesn't move at all. Okay, and in particular today, we're going to explore a specific type of model called the ring model. Okay, and this has largely been successful for I think 30 or 40 years, describing modules in the visual system. In particular, that processes angles. Okay, so if you look out at the visual world, okay, in the room around you, you look at objects, okay, they're made up of, if you zoom in very closely, right, that a lot of them have edges to them, right? And those edges have some angle orientation, okay? And if you were to draw those objects on a piece of paper, you would have to use lines essentially in order to draw these objects. And so the idea is that you have neurons that respond preferentially to particular line segment angles in the environment. And this is actually one of the first sort of sensory tuning properties discovered in mammals by these people, Hubel and Wiesel, about 60 years ago. Okay, so the idea is that the x variable now just represents the preferred angle that a particular neuron is processing. Okay, and we're going to take a weight function that is just a function of the difference between the preferred angles of two neurons. Okay, and we assume that we have a periodic system, okay, with the following weight kernel, okay, W bar. And because I can just write it like this, okay, I can just write it as a single argument. And that's going to be scaled by 1 over pi so that the normalization works out nicely. W0 plus 2n equals 1 up to infinity. Wn cosine of 2nx. Okay. And Wn is going to be some real number in this case. So the idea is that this function W is going to look, something like this. It's going to be an even function of x, and it's going to be locally excitatory, okay, and distally inhibitory, okay? So neurons that like the same angle will tend to excite each other. Neurons that like different angles will tend to inhibit each other. And this is going to sharpen any of those line segments that get processed by this particular network, okay? So in some cases, we have what are called stationary bump solutions, okay? And we can write them as U equals big U of x, okay? So rather than U being a function of space and time, we assume that U is just a function of space, okay? And if I draw as a function of x, this is 0 up to pi here. We have some bump. This is our bump here, okay? U is a function of x, okay? And if we look back at our equations here, if U is not a function of t, then this is the only part that matters. And if we assume that we also have no input at all, then essentially we just have these two terms here, which then we can write out as a stationary equation, okay? So given no input, I0, and noting that du dt equals 0 for U equals U of x, okay? Then we have U of x is equal to the integral from 0 to pi W bar x minus y f of U y dy, okay? Now you could solve this equation numerically, okay? But we can actually use this Fourier expansion. We can exploit this to make simpler problems. And in the case where your weight function is only involves maybe a few of these coefficient terms, okay, then you just have a low dimensional nonlinear root finding problem to solve to find these solutions, okay? So it turns out, okay, you can show that U of x then in this case is equal to A0 plus the sum from n equals 1 up to infinity an cosine 2nx is a solution, basically by assuming it and plugging it in. Because of the translation symmetry of this problem, if you have a bump here, you can also shift it around and that'll also be a solution. And that would be revealed also by the stability of this model that we'll talk about later, okay? So, so we could do that, okay? But an alternative approach is to use weakly nonlinear analysis and show it using sort of perturbation theory that you get bump solutions like this. And this is where we're going to go to back to our method of multiple scales approach, okay? So alternatively, we can show solutions perturbatively, okay? So we'll assume, first of all, that there exists some uniform solution U is equal to something I'll call U bar, which is constant in time and space, okay? Such that U bar then is equal to f of U bar, the integral from 0 to pi, W bar x minus y dy, okay? And if we use this kernel here, right, all these cosines are going to integrate out, and the only thing we're going to be left with is W0, okay? So this uniform state is actually going to be given by this rather simple implicit equation, okay? U bar equals f of U bar W0, okay? So to determine the stability of this equilibrium, we can set U of xt is equal to U bar plus epsilon U of x e to the lambda t, okay? And this is a common approach for nonlinear spatiotemporal equations. How do you study them, right? Because in general, it's hard to just find solutions from scratch, okay? But a lot of times you will have a stationary sort of flat solution, and you want to know if there's any instabilities of that stationary flat solution that form more interesting, spatially varying solutions, okay? You're just assuming that you can perturb by a solution that looks like this. It's a separable function of x and t in this case, okay? And will linearize. And then you're going to get an equation that describes the evolution of modes that look like this, and which ones are sort of the most unstable. The ones that are the most unstable are going to have large positive real parts of their eigenvalues, okay? So we just have to plug this in and Taylor expand like we have with a lot of different methods, okay? And we take f of u plus epsilon U of x e to the lambda t. It's approximately equal to f of U bar plus epsilon f prime U bar U of x e to the lambda t plus order epsilon squared stuff, okay? Du dt is equal to epsilon lambda U of x e to lambda t. And so if we plug this all in, what we get is epsilon lambda U of x e to lambda t equals minus U bar plus minus epsilon U of x, okay, e to the lambda t plus integral from 0 to pi W bar x minus y f of U bar plus epsilon f prime of U bar U of y e to the lambda t dy, and then plus order epsilon squared stuff that we don't care about. So for now, we only have to deal in order 1 and order epsilon things. If we go to order 1, we should not get any surprises, okay? Because we should just return to our homogeneous equation that describes our homogeneous solution, our flat constant solution. And that's indeed what we get. We get, in that case, 0 is equal to minus U bar, and then just this term here, plus f of U bar integral from 0 to pi W bar x minus y, okay? And this is our stationary constant solution, okay? Now, just like when you're doing, phase plane analysis and you want to know the stability of fixed points, okay? Here, instead of having a plane, we have, an infinite dimensional system. right? We just, um, we have variations in X, right? And so you could have any shape of X here. It's not just like when you have phase plane problems and there's only sort of two directions you can perturb. You can perturb by, having a function of any shape you like, right? But nevertheless, this is still an eigenvalue problem, right? So if we look at the order epsilon terms, we have lambda u of x. It turns out e to the lambda t appears in front of all of our terms, so we can just remove that. And we get lambda u of x equals minus u of x plus the integral from 0 to pi w bar x minus y f prime of u bar u y dy, okay? And we're going to call this thing L u of x. This is a linear operator acting on u in this case, okay? So this should look like an eigenvalue problem. We have an eigenvalue, an eigenfunction, okay, and equal to some linear operator. So we want to figure out what are the functions u that satisfy this equation, and what are their associated eigenvalues. And once we look at those eigenvalues, we'll be able to tell whether this stationary state is stable or not, okay? And if there's instabilities, what emerges from those instabilities? What does it look like, okay? Does it have some, regular features to it? And this is a common technique used in pattern formation, both for integral differential equations and also, nonlinear PDEs, okay? This is very useful in general in nonlinear dynamics of spatiotemporal systems, looking at this sort of spectral problem that you get by perturbing around a flat solution. Okay. So I'm gonna wrap this up, and then we'll be done for the day. So the idea is that L u of x has eigen solutions. Okay. Un of x is equal to cosine 2n of x. Okay. Or we could also use sine of 2n x as well, okay? So these, these form a complete set if we were to take all of these, okay? I'm doing a little bit of an abusive notation here. I'm just going to look at in detail the eigenvalues associated with this. But the eigenvalues associated with this function are also the same, okay? So if you
Is this
plug this,
for any firing, right? For any F?
well, yeah, so it works for, yeah, it should work for arbitrary Fs, okay? Because the F then just tells you the form of the eigenvalue that you should get in this case. Yeah. So if you plug this in, right, and the reason for that is the structure of this operator, right? It just depends on this weight function, and because we used a particular weight function that's just separable into into these trig functions, right? And it's homogeneous. You can use trig identities and basically pull out cosines of 2nx, 4nx, and so on. And so when you plug this function in, and work out from it what the eigenvalue should be, you get lambda n equals -1 plus f prime u bar wn over 2 for n is any integer, okay? And we can show that by showing if I plug this in, I get cosine 2nx is equal to minus cosine 2nx plus f prime u bar wn over pi, the integral from 0 to pi cosine squared 2ny dy cosine 2nx. Okay. So when you clean this up, you get minus cosine 2nx plus f prime of u bar wn over 2 all times cosine 2nx. Okay. And similar for sine 2nx, you essentially get the same thing using trig identities. Okay. So this tells you, and I'm just about done here, that we have a bifurcation parameter in our system. Okay, so if we look at this eigenvalue here, what's going to make that solution unstable? Well, it's if at least one of these eigenvalues has positive real part. Okay, so that means as we change f or as we change u bar, okay, then that is going to potentially bring one of these eigenvalues positive. Okay, so our bifurcation parameter I'm going to define here as f prime u bar over 2. Okay, and essentially as mu is varied, okay, to be greater than 1, then instability occurs. Okay, you go through a bifurcation. Okay, so for mu small enough, lambda n is less than 0, and our equilibrium is stable. Okay, that means that nothing happens in this neural field. You just have a flat activity. Everything's sort of boring. Okay, but maybe that's fine. Maybe that's you want the activity to be flat until an input comes in. Remember, this is in the input free case, so it's not processing anything. Okay, and then as mu increases through, in this case, mu c equals 1, the equilibrium destabilizes via the largest Fourier component. Okay. All right. So that's what we'll study next time. Okay. We will examine this instability. And the idea is that for whatever Fourier component is largest here, okay, so I guess in this case, yeah, it should be to be greater than 1. I guess it should be greater than 2 over Wn, excuse me, 2 over Wn max, okay. Then we get this instability essentially. So for the largest one here, this value is going to be the smallest, okay? And as we pass through it, we're going to destabilize the Fourier component, and the instabilities that you're going to get are going to have the frequency of the Fourier component that is the least stable in this case. All right. So so next time, what we're going to look at is what happens as you pass through that instability, and in particular, sorry, this should be 1 over Wn here. I'm rushing through this. And in particular, the fact that you can describe exactly the nonlinear destabilization using an amplitude equation approach, similar to ones we've used in other multiple scales examples. Okay, so I know I said I was going to end early. I don't want to keep talking too much. Are there any questions about this so far? All right. So I'll recap that at the beginning next time, and then we'll go through the procedure of deriving the amplitude equation essentially for this system as you destabilize those Fourier modes. And that gives a nice example of pattern formation, which is applicable not just here, but to a lot of different nonlinear PD type models as well. Okay. All right, so that's enough for today. Don't forget to do your FCQs, and I'll see you all on Wednesday.